Oregon State University, USA. Now she is a professor at the Faculty of Liberal Arts and Science, Kasetsart University, Kamphaeng, Thailand, and laboratory leader of biophysics in Japan at the Center of Excellence on Agricultural Biotechnology, Kasetsart University, Kamphaeng, Thailand. Her expertise is soil physics, water relations in plants, and soil plants and atmosphere patterning.
Ladies and gentlemen, please welcome Professor Suntaree Yingjajaval.
Oh, good.
Morning. First of all, I would like to thank the organizing committee for giving me the chance to talk today. They want to know about my work, which is to my surprise or unexpected, because most of our work is sort of, people would say, what is she doing? Or complex, why she has to measure so many things. So I think this is a chance for me to tell you what it's all about. All of our work is within the framework of soil, plant, atmosphere continuum. We measure the plant in context with the soil and the atmosphere. We never study it by itself. And most of the study is about flow. The exchange of gas, exchange of water, and that kind of thing. So there's always dynamic in our thinking. Now, to do that, there's some kind of, we follow the sort of basic idea, and this is based on the thermodynamics. Okay. We would just simply say that plant is an open system in an irreversible, non-equilibrium, and things going on in a non-steady state. So these are all big words. But what we are saying is that, so a plant exchange matter and energy all the time. So it's a system that unpredictable. You cannot say what the future will be. And it's irreversible because it's a flow, there's a flow. So there's change from one point to the other, and you cannot get back. It's like, you will never get young, because the second law of thermodynamics will say that. Now, because it's an open system, you can never talk about equilibrium. In my work, I never say equilibrium, not ever, because it's not possible. But you are saying that if there's a flow, and the flow in rate is equal to flow out rate, then you have a steady state. But most of the time it's not steady. Okay? So in studying plant, we use the irreversible thermodynamics, which says that flux is the product of a coefficient called conductance and the driving force. So in studying it, in short, we will say dynamics. And so we are not looking at the difference per se, we are looking at the pattern of change over time. It's a time series kind of study. And we use a lot of these simple equations, say, okay, so the flux of the rate is just the product of some constant times the difference in the potential that's moving. Okay? And we use a continuity equation, which is conservation of mass and energy, saying that you need to know what's flow in and what's flow out. And we need to sort of define our control volume. So when I study plant, I will say, okay, this is is my control volume. I need to know what the boundary is, what's going on in the soil, what's going out into the atmosphere. Now, so if there's a flow in greater than what's flowing out, then they have to some change in the control volume. It's either increase the volume, it's increase the concentration or the storage. On the opposite way, if the flow is smaller than flowing out, then the system gonna shrink or lose something. Okay. Now, I start to see some blank expression there. And this is the reason, we're working using all this in our work. But it's very difficult to explain it to people. Dynamics, dynamics will change. But they never really embrace and put this in when they wrote the proposal or when they put it into the experiment. Somehow they want to fix things, they want to put a measurement and say, okay, I'm going to compare these two treatments. We never do that. So I'm going to tell you today how we handle the dynamic nature of plant. And the best way is to show you by illustrate with a case study. And this study is about the mango tree, and it's about the fruit disorder that is related to the flow and the calcium supply. Now, this problem is requested by the farmer school of Suntaree. And they said, please find the cause of this disorder. As if we know that maybe we can make some correction. And the four main problems are the gamboge or the gambogia, because they first find it in Cambodia. The gamboge, this is the oozing of yellow latex, the translucent flesh, different kind of aerial properties, and the cracking, and the wrinkle polycarp. The wrinkle polycarp is straightforward, it's just dry out, so we're not interested. We don't need to find the cause of it. But you can see that this part are external symptoms, so it's easy to just pick out and throw it away. But what's inside? Growers exhausted all of their techniques try to separate the bad one from the good one. And it's not easy to do that. No sure way. And it's very kind of a big loss, because then the whole shipment of mango seed can be returned if the number percentage of disorder exceed what they agree upon. So it can be a disaster for the growers. Now, because this is that problem, so they are so willing to share with us what's their observation. And this is what they say, that all of these disorders seem somehow connected with rainfall. And they said, okay, both, especially the gamboge and the translucent, will occur when the rain comes after a dry period. And this is particularly intensified 2 to 3 weeks before harvest. And the fruit in the shade has more disorder than the fruit in the sun or in the open. Now, all of these are keywords. If we find any explanation, it has to comply or explain agreeable with all these keywords. This disorder problem has been for a long time. It's not new. And many studies have done before us. The common explanation would be, when it rains, the water seeps into the fruit and cause the fruit to crack. Look, but this one, if you say that, then the fruit in the sun will have more disorder then, because it's open to rainfall. It receives more rainfall. So it doesn't logic. It has no logic to that. Okay. Mangosteen normally in a normal year would flower early in the year in January, and it's a Pathom, so it's a set fruit underway. The development period is about 12 to 15 weeks. So when you start to see the spectrum of pink color on the epidermis, then it's ready for harvest. And for the terminology, the outside we call it pericarp, and the flesh we call it aerial. In terms of botany, it's outgrowth of the seed. Alright? Then when I looked at it, I said, okay, so where's my control volume? That's how I set up the system. So the system can be just the fruit itself, or we can include the leaf too. But whatever that we include in it, we have to be accountable for what's flowing in and what's flow out. So we did have to have several measurements there. Now, in order to try to get enough information to satisfy all those, match with all those observations, we put up the scope of the study. And we have to measure all of these 8 items. First of all, why is 2 to 3 weeks important? It has to do with the size change or the development of the fruit. And how much flow in and how much flow out. And ruby, if there's a flow, we need to find the potential difference. Can we measure it? And if there are cracks, you need to say, okay, how could it crack? There must have been some turbo. Can we measure the turbo? Is the magnitude large enough to cause the cracking? This kind of thing. And all of this happen in the environment. You have to detect or record the environment too. So first of all, we set up the kinetic condition, the station. We have all, of this radiation, the terminology of LDPD is an important one because this one will dictate the loss of water from the plant, so-called LDPD, and we also have information on the rainfall. We install sensor in the root so that we can measure the soil water status, and we also have the information on the in-canopy magnetic condition. So the soil is show kind of a sufficient water in there, high magnetic potential. That is because the grower will sprinkle most of the development period of the mangosteen. So when we say it's dry, it means the air is dry, not the soil. Now the measurement we made on the plant, we made on, we call it diurnal measurement, and this is because plant is subjected to a dynamic change every moment of the atmosphere. How to handle the plant response is to accept that this is a dynamic condition. So we measure the kinetics on an hourly basis throughout the day. And then we make the measurement of the plant every hour of the day. Okay, so that we can see the pattern of change in the plant. The first thing we measure is the sap flow. So we put in the sensor in the main branch and the secondary branch, tertiary branch that leads to the fruit and the leaf. So it's set up there. Many sensors in the various size of the plant, and to the fruit on this side, we can also measure the transpiration and photosynthesis rate. On the fruit on this side, we measure the change in the size of the fruit. Of course, it would be nice if we can measure everything in one fruit, but the size of the equipment just limits us this way. So the diagram shows you the many sensors that put in throughout in one plant, one tree. Alright? We have the diurnal data. It is, by the way, it's not my intention to explain all the details, just you to follow the ideas. So we have this daily data. And the interesting point is that one day there's a rainfall in the middle of the day. And we can see that the sap flow simply stops. So when it rains, no flow in the branch, in the main branch, no flow in the tertiary branch that leads to the leaf. So you say when it's rain, water flow into the fruit, I can see that. So then the diurnal, you can average it out on a weekly basis. So you can see that as the fruit is young, there's a high, when the early part of the year when it's dry, then there's a large flow in the branch, and then it sort of gradually slow down as they appear to have more rains and towards the latter part of the fruit development. One thing is that if there's a flow in the branch, the air has to be dry. Then the fruit and the leaves and every part of the tree start losing water. Then water will move into the field that, remember the control volume. To have something move out, then something can move in. Alright? Then we need to also say, okay, what's happened to the fruit in the shade? So another year we just, measure the fruit in the shade against fruit in the sun, and to just overread it, we put a plastic wrap up on the fruit, no loss, no transpiration loss. Then we can clearly see that the red line shows the fruit in the sun has a higher flow rate in the branch than the fruit that in the shade. So the shading is the fact is to slow down the flow in the tree into the fruit. And if there's no loss, there's simply no sap flow. Alright, we make the measurement of the leaf, the subtending leaf, and we make the measurement of transpiration photosynthesis on each the fruit. And we have daily data like this for 15 weeks. And we average this and give us sort of the idea of the fruit, you lose water, transpiration is high, it is young, and slowly, increase the rate, the same rate of respiration. Now on the other side, we measure the size change with a dendrometer, and we can see the change in size, slowly shrinking throughout the day. But at the end of the day, the fruit becomes larger, like that. So throughout. The point is, during the time about the middle of the fruit development, 6, 7, 8 weeks, is the time when the fruit has the largest volume change, expand the most. And by the time there is 2 to 3 weeks before harvest, all of this growth seems to be stopped. So the size becomes stable, constant. Now, we put all of this together. We have the data on the climatic condition, we have rainfall, we have what flow into the branch, what's flowing out by transpiration of the leaves of the fruit here, the leaf of the fruit. And so we can make a bottom sheet, so to speak. And we are talking about a net flow of up to 10 grams or 10 cc per day during the daytime. But the fruit change is shrinking during this time. And the size of shrinking is, we are talking about only 1 cubic centimeter. So the data still has some discrepancy. We have to work on it. Either the sap flow gives us an overestimation, or the transpiration that we measure are underestimated. We don't know. We have to work out quite a bit. But one thing for certain, the flow in the branch will slow down, coincide with a lot more rain. There's rainfall in the, so now you can imagine that if it rains all day and all night, what happened to the mangosteen tree? It just stand there and all the circulation simply stop. No flow, no transpiration, no flow, means no supply of nutrient to the leaf. And even if the leaf can photosynthesis, for example, if it can, because maybe there's not enough sunlight, but if it can, there's no flow, translocation to move the sugar to other part. So rainfall is actually very bad. Because if you're talking about 7 days, 7 nights, So summary 1 All those keywords, we already have the data. So it's the dry air, and when it's the set, the flow rate. And we also test that the fluid in the canopy is because it transpires, so the sap flow is smaller. Alright, next, since we have the flow, then we have to find evidence for the potential difference along that flow path. So we measure the total potential, we measure the osmotic potential, and we calculate the turbo potential. We have daily basis, on the daily basis we have data. Each of these points is one microscheme, it's one sample. So at least in a day we have about 12, at least 12 fluids, and we multiply that by 15 weeks. So we almost ruin that portion. We take out several, maybe 1,000 fluids out of them. Anyway, what we saw, to my interest, really, I'm so excited to see this data, is that during when the fruit is still expanding, we can see a higher water potential in the leaf than in the fruit. So there's a flow from the leaf to the fruit, there's direction of flow. But when the volume starts to slow down or stop, then there's a reverse direction. Then the fruit has a higher water potential than the leaf. So indicate to me that now you have water flowing out of the fruit to the leaf. You will say, is this possible? The same with the solute, and with the turbo potential. The solute says that there is something to translocate from the leaf to the fruit, and there's enough pressure to push it through in the flow. The fruit component is of most interest. We not just the peduncle, but also get into various parts of the fruit, the polycarp and the aril. The same thing, at the beginning when the fruit is still developing, the leaf has higher sugar than the aril and the polycarp. So there is sugar to be transported, and there is turbo to transport it in the flow by 6 elements. But as the fruit starts to mature, then there's a reverse of direction. So this is where I said, is this conducting two? Are they still connecting to one another? If they are connecting and it's a passive transport, then the fruit will start to lose sugar to the leaf. So they need to have some kind of a change in the cell wall. Okay. But the one thing that we have a good proof is that now we can see the turbo potential in the aril. This is about 6 bar of pressure, enough to crack the polycarp. The important thing is that this aril consistently has a higher turbo than the polycarp. So you have a pushing force from the aril to the polycarp, which can cause this cracking. Okay? And the cracking comes also with, if it's serious, then the latex duct rupture, and we have seen the translucent of this order. So, you can look at the rupture of the latex duct, and this is typical. You can see the bruising and on the polycarp from the pushing of the aril turbo there. So, to make sense of all this, now is the scenario is that, okay, when the fruit is still expanding, water moves in for transpiration, water moves through that in the translocation. So all of this water is used to push out the side of the fruit. So turbo can remain constant. Definitely the problem of disorder during this time of the fruit, because all the turbo has been absorbed by the increasing in size. But when the fruit stops growing or stops expanding, then there's still need for water to move sugar in. But this water has no way to go because it cannot expand anymore. And the transpiration rate as the fruit gets old is reduced greatly. So this water has to be returned, going back a reverse flow, which agree with the potential difference that we have measured. So this all seems to be quite good. So as the fruit mature, turgor build up. Okay. So in the second summary is that so as fruit matures, turgor level increases in the fruit, and that is the difference in the turgor of the area periodica. Now, so far all of our experiment study would give you a sequence of thought. Okay, if we have low BPD, the air is moist or even have rain, then we have low transpiration, we have low subflow. And we measure the turgor, so we prove the turgor exists. So they say, okay, so turgor is natural to mangosteen fruit. But then why not every fruit show this order then? So now we have to investigate on the role of calcium. Okay, there's tons of literature talking about the importance of calcium. But in short, calcium is kind of problem because it can be moved only with transpiration slowly. Okay, and calcium related to cell wall strength. That is the role of calcium. So we say, okay, Sumitra, now we have established the flow, but we have to connect it to calcium somehow. So we set up another experiment, and we said, okay, let's decrease the flow rate artificially by changing. Okay, so this one, my good colleague here, Sumitra, good. And at the same time, we just said, okay, what about if we reduce the transpiration by wrapping up each fruit? So this is the field experiment, looking good for about 5 weeks. Then the wind goes away. So we have to do it like this. Not perfect, Then another option, we have the shading by the tree. So Sumitra, with her good relationship, she will be able to ask the grower to come down on the tree. But you look at it, it's not our orchard, and it has been like this. So we're not talking about randomized design, Can you do it? But Sumitra, to be faithful, she still keep 10 trees for her statistic. So despite all the imperfect of the setup, she managed to find that if you have a shading, then the percentage of noble fruit is decreased, and the percentage of the gambles increased. In one of the orchards. The second one doesn't seem that way. But if you look at the second one, the important point is here, the large fruit suffer the most. That's because Sumitra has been working out and she cannot find the explanation until she separates the fruit size. The large size means that if you need higher supply of calcium, so the disorder seems to intensify. Now, she analyzed calcium in the whole fruit. You can see the difference. Not to give up. She separated pericarp to the areola. Not to give up. Data still not good. So she go down to the cell wall part and even go down to the pectin. I have to admire her perseverance. Really hard work. So she used all this extraction to separate various fractions of pectin, and she take out the hemicellulose and all kinds of things. So if she used the 6 extraction, she come up with the total amount of pectin and hemicellulose in the cell wall. And this is the graph she gave me. It's natural, you will plot it this way. But then your idea will be fixed and say, okay, so there's a difference between orchard 1 and orchard 2, and you try to explain it. And I told Sunita, no, this is not my interest. I don't have, there's many variables between these two orchards. This is not my main objective. I thought it this way. It's 1-to-1, black. The unshaded pericarp will consistently show a higher cell wall material, the pectin, than the shaded one. So the shading did affect something in the cell wall. And for her data, she also measured the calcium content. So you can see the calcium in the pectin, not the whole fruit, but in the pectin. If it's open fruit, not unshaded, then you have a higher calcium. So there's something here. And this calcium is in the form of ionic bond that show a higher calcium content in the pericarp. But arrow is a different story. Anyway, her data, to group it in another way, is to group between the normal fruit and the disordered fruit, and it's clearly show that calcium in the normal fruit has a higher content than in the abnormal one. Okay? That's in the pericarp. The arrow is confusing because now the calcium content become higher than in the normal. This will need a lot of explanation, which we will go on. But anyway, so her result show that the shading did have effect on the construction of the cell wall and the pectin. Okay. The second experiment we have is about the wrapping of the fruit. So this one is a couple of trees in the open. And we just wrap it up from the beginning of the development, something like this. So what we are doing is, okay, we like to know that if you wrap it for 1 week, something like this, and then take out the wrapping and go to the next one, at what time that the fruit is most vulnerable to this wrapping. So we do this, on and so forth until the end. And this wrapping is a material like the pulp. It allows moisture to move out, it can transpire. So we do that. And the result is still analyzing, but the best way to show it is that if the wrapping occurs during the most volume expansion period, then the disorder percentage seems to be increased. Okay. So if you stop the transpiration at that time, means that you stop calcium supply maybe. So what we do, we analyze the calcium supply. So the calcium in the pericarp of the unwrapped fruit show a consistently higher content than in the wrapped one. And this shows the higher one only when you wrap it during the young stage, before the fruit mature. You can see that. Anyway, another additional information we got is we use the aerial extract, and then we measure the rates and we measure the pH, both by us and by Dr. Suntaree. We can consistently see that the normal fruit has higher rates, means that higher sugar than the translucent aerial, and it has a lower pH. The pH is something to do with the cell wall extension, shade of cell wall. Anyway, so to us, this now point to a condition that the translucent somehow to do with the ripening process, not just cracking of the cell wall. So in order to understand that, we need to have more insight into the pectin property. And this, is work by biochemists. So we just follow the idea and try to see if it's fit into our thinking. Now, they said that the pectin in the cell wall the major component would be homogalacturonan and rhamnogalacturonan 1 and 2. And all of these are cross-linked to form a network. Now, the homogalacturonan are ionic bond, forming fixed cross-linked together by ionic bond of calcium. Whereas the Rg2 are ester bond by ester by boron. And this is why calcium and boron are necessary for cell wall construction. Now, they said that when the pectin, the homogalacturonan was constructed inside the cell, they are mostly in the form that ester by methyl group. But when this part moves to outside into the cell wall, part of it will be removed of the methyl ester by the enzyme there. And once the metal is removed, then if there's enough calcium would be moved into the free carboxyl group and form the ionic bond. This kind in agriculture is just called simply as calcium pectate. The calcium pectate part is the one that makes cell wall flexible because the ionic bond allows the lamellae to move past one another and to resist the push. So a calcium sort of gives it like a spring somehow. And this part is most concentrated in the middle lamella and 3-way junction. Now when the cell breaks, it is that the force pushing on the cell wall and then the middle lamella give way for the cell from one another. So you need to have a strong elastic wall of the middle lamella there. This one is a very unique picture to show you that, to remind you that we are talking about a fruit development of 15 weeks and during expansion is 11 to 12 weeks. We are talking about new cells are constructed all the time together with the cell wall. So during this cell wall construction, there is a need for supply of calcium and boron all the time. So you can see that this is the example of cell wall of the tomato fruit, and the black spot is the pectin without the metal, so it's kind of elastic. And you can clearly see that it's not uniform. Sometimes you have a region where you don't have the calcium pectate, and even the two cells close to one another are different things. So we are talking about a time when the cell wall is constructed and it will need calcium, but there's a rainfall and there's a low supply or no flow. Then calcium is not delivered to the point where it's needed. This is the picture there. So the cell wall property can vary depending on the local supply of calcium and boron. Now, with all of this in hand, we now speculate. Of course, it's wrong with the gambols and fruit cracking. All of this, we say that by lacking calcium pectate in the pectin, then the cell wall becomes stiff and cannot handle turbo that well. So this cell wall will have a failure plane, and it will just break the cell-to-cell adhesion. And that's why we have the cracking there. But the translucent phase is more involved. This one involves a process of ripening at the end of the fruit development. When it's ripening, all this pectin network will be cleaved by the enzyme polygalaxyronase. Okay? And to free its component out and so make the tissue soft, so we say. But the activity of this enzyme will be hindered or slowed down if you have if the system has low calcium pectate. So this network will remain intact, and this is what show up in the translucent flesh. So we are saying that the translucent flesh is just the area part that has not gone through ripening process. Now, so by thinking about, you construct cell wall all the time, there's a need for calcium all the time, but that will be up to the delivery of the calcium. So at the end, people say, okay, so the study, so can we correct this disorder? The obvious answer is no. Because we are talking about matching the supply of calcium to the demand throughout the expansion period. And the supply is controlled by transpiration rate. And transpiration rate is up to the changing environment. So we may not eliminate the disorder, but we can minimize it if we can, put practice in supplying calcium and boron. So premium grade is possible, we can do it. Now that we know what's happening. Okay, that's the case study. My real point is that, so this is what we got. We said, all right, from my experiment, we can say that low BPD or rainfall leads to low transpiration, leads to low cell flow, and leads to low calcium content. This one and is more susceptible during the expansion period of the fluid. This, the black color, the black front here, we know for sure because we have data to support it. We say, okay, so this theory, low elasticity of cell wall, I haven't proved that yet. I don't know if I can do. But the second one we know is that there is a turbo gradient exists to push deposit cracking. So we are now saying that the cell wall lamella that is during construction, if any layer of that has low calcium supply, then that's the weak point in the cell wall. So now you can expect why some fruit has the cracking and not the others. It depends on whether when they need calcium, it has been supplied sufficient or not. Okay, this actually is the point of my talk actually. So I said, okay, people say, oh, why do you have to measure so many things? And besides, you don't have experimental result. So how can I believe you? I don't even show you the test of difference that this treatment is different from the other one. Why don't I have a solid statistic? Because I'm working with a dynamic condition. I'm working with atmosphere which is not well defined. I cannot order rain. It's come as mercy, its own mercy. And decide, why just one tree? Why don't you? So I just don't have that resource. But what I did, I built up story. I have preponderance of the evidence. Preponderance means superior number. I have so many data that they lock together. And this is the only way to explain this data. Okay? So, I like to say this. If Charles Darwin was alive today, he would never have won Nobel Prize. Why? Because he never did one single experiment. He never know about experimental design, has no statistic. But what he did is gather data, many of them, during this several trip. His greatness is in connecting the dots. And he sees the connections. Now today we know, this is what network inside one bacteria. Each point is one compound, one chemical. And we even know now how these chemicals react and they catalyze one another. So are you telling me that if I know one gene that control the formation of one chemical. Now, has the effect change in the whole land? You say that? Okay, but I ask you, if you change one chemical, now, what parameters you gonna measure to show that you have changed the whole system? That's the most important point. What parameters you have to for your check, for your test of difference? So we are working on a complex and dynamic system of plants. Let's accept it. It's difficult to do, but at least you will find solutions. If you keep it simple, you go nowhere. So, fellow researchers, young ones, let's be brave. Move to the next level. Okay? Try to explain the question of how. Right? You can see that all this work is not by itself. It's not an island. So we need all these researchers in our team, in the lab, and my good colleague, Dr. Suntaree here, a good boss and associate boss who gave us all the resources that you have seen. All the equipment, all the researchers, all the money to run it, without which we cannot do. So I thank you, all of them here. And thank you for your time.